Hey students, welcome to Sustainable Energy. I'm Rudi Schlaf, a professor at the Electrical Engineering Department at USF. This is part 2 of the nuclear energy segment. In part 2 we will discuss the use and feasibility of nuclear fission, the risks and benefits of fission, nuclear fusion and fusion reactors.
Like with any fuel-consuming power plant, an interesting point is how many uranium resources are there and what is left, and how long can we sustain a nuclear energy program on them. This table shows a list of countries and how much uranium they need per year. And so we come up with a total demand of 66,877 kilotons per year. On the other side, we have the uranium producing countries. Here we have numbers that give us an estimate how large their resources are that we can expect to get out of them. And so the total resources are 2,643 kilotons. Now, the current consumption at the current level worldwide is about 67 kilotons per year. So this means that if we keep going at this rate, we would have uranium for about 40 years. An interesting aspect is that most of the countries we have on the producer side are not the same countries that we have on the consumer side. So we have a similar situation like with fossil fuels, where there are also only a few countries that produce it in significant amounts, and they usually are not the main users. We just saw on the previous slide that uranium may only last 40 years with the current technology. This means that uranium will see its Hubbard peak probably earlier than fossil fuels. This hardly makes it a sustainable technology for power plants. However, there are ways to extend the life of the uranium resource, which is through transmutation of non-fissile material into fissile material. If you remember, most of the uranium resource is uranium-238, but we can transmutate it into plutonium-239 if we expose it to neutrons. And this is used in so-called breeder reactors, where the idea is to breed fissile uranium from non-fissile uranium. The way this is done is by putting a breeder blanket made from the non-fissile uranium-238 around the reactor core that runs on enriched uranium rods. So we have our chain reaction, and neutrons hit the breeder blanket, and then in the breeder blanket transmutation makes plutonium, which then can be extracted and can be used as fuel. So with this technology, one could probably extend the resources by a factor of 30, and that would put us at 1,200 years, which would make nuclear energy a much more sustainably looking type of power. The issue with this technology is that one cannot use water to cool these reactors, because water acts as a moderator that slows down the neutrons. This is something one wants in a conventional fission reactor, but in a breeder reactor we want the fast neutrons to hit the breeder blanket, and so we need to use a different coolant. Coolants that are considered or in use are sodium, potassium, NaK. One can also use liquid sodium. And so these materials are in a very hot and liquid state, and they like to either react with water or they are corrosive to metals, and that poses an entirely different set of safety issues when it comes to these reactors. It should be mentioned that there is another breedable material, thorium. Thorium can be bred into fissile uranium-233. And so if we would add in the thorium reserves into this mix, one could yield maybe another factor 4 in resource lifetime. So this would put us into a few thousand years and make this a fairly sustainable energy technology. At this point, only India pursues thorium-based reactors, because India is the major thorium producer right now. This slide shows a map of the locations of nuclear power plants across the United States. You see here that most of them are concentrated in the eastern half of the country. There are 100 individual reactors in operation in 62 power plants, so several of them have 2 or more reactors. They produce 91 gigawatts in total. It's interesting to note that the electrical capacity of these 100 reactors is only 10% of the total electrical capacity of the United States. And you see that natural gas and coal have the lion's share. But if you look at the share of the electricity output of nuclear power plants, you see that they have a 20% share. Now, why is that? The reason for this is mainly in the fact that nuclear power plants run much cheaper than coal-fired power plants after they have been built, because there is very little fuel to be bought. Gas, on the other hand, has a much smaller share than the capacity, because gas is only used during peak periods. Coal is another baseload type of electrical power provider, and so coal has almost a 50% share of the total generation. It's interesting to note that there hasn't been any new groundbreaking of nuclear reactors since 1977. This was mainly due to the 3 Mile Island accident in Harrisburg in 1979. 4 new reactors are currently approved, and this is thought to be a renaissance of nuclear power in the United States. However, it seems there are many regulatory hurdles to overcome and financing issues before these reactors might be built. As for any energy source, cost is an interesting factor. Here's a table of levelized cost of energy that is issued by the Energy Information Administration in certain intervals. This one estimates the cost for 2019. And so we see here advanced nuclear is listed at 96.1 total system levelized cost of energy. The units are $2012 per megawatt hour. So if you compare this with the numbers for the competing power generating technologies, if we look here at fossil fuels, these are in the blue box, we have values that are 50% lower or 50% higher than nuclear. So we can say that nuclear is in the same ballpark as conventional fossil technology. If we look at the renewables and sustainable energies, then we see that wind offshore is, for example, twice as expensive, solar thermal 2.5 times more expensive, photovoltaic panels is in the ballpark of fossil fuel, a little bit higher than nuclear. If we look at onshore wind, then it seems it is cheaper than nuclear, same with hydropower. So it seems the cost of nuclear power plants is within the ballpark of all the other energy sources. When it comes to the energy return on investment, the EROI of nuclear power technology, the estimates vary widely. This graph is from the meta-study that we encountered earlier in the other segments of this course. And you see here that they assign a very wide range of EROIs to nuclear technology. You see here that various studies assign a wide range of EROIs to nuclear technology. As usual, the EROI depends on the boundary conditions that are used in such studies. And so the question is whether waste disposal is included, whether long-term storage in ponds is included, whether cleanup after major accidents that apparently occur every few decades are included, and so on. Probably the same is true when levelized costs are estimated, because no one really knows at this point how much waste disposal will cost and all these issues. So all the numbers that are about the future of nuclear technology need to be appreciated with a certain level of uncertainty. When it comes to the risk of nuclear power generation, it's interesting to compare its fatalities record with the other major electricity generation technologies. I found this interesting paper where they compared the number of fatalities per year per gigawatt of generation capacity. They compare coal, oil, natural gas, liquid propane gas, hydro, and nuclear. At the point of this study, which was published in 2000, there was really only one major nuclear accident that made it into this statistic, the one in Chernobyl. Now this compares with 133 events in coal, 295 events in oil, 88 in natural gas, 77 in liquid propane gas, and 13 in hydro. And this is from 1970 to 1992, so over 22 years. And the events that they list here, they range in fatalities as listed in this column. So in the case of coal, we had 133 events where between 5 and 434 people died, so that makes it a total of 6,418. And one can say that coal produced 0.32 casualties per gigawatt per year. So oil is pretty similar, 0.36 casualties per gigawatt per year. Natural gas is 0.09, and liquid propane gas, and I don't understand right now why, has a much larger fatalities rate, 3.1 gigawatt per year. If you look at hydro, it's 0.8, so hydroelectric power seems to be more dangerous than coal and oil and natural gas. And if you look at nuclear, we have 0.01, so this is 2 magnitudes better than the fossil fuel technologies. So on this end, nuclear seems pretty good. So these fatalities, they are direct fatalities. They occurred directly during the accident, and in the case of fossil fuel, explosions and fires were the main reason, or in the case of coal, of course, also mine collapses. When it comes to nuclear, the 31 fatalities in Chernobyl that occurred immediately during the accident or in a very short period thereafter, they are radiation exposure deaths mainly. If you read accounts of the accident and how first responders responded, it could be said that probably several of these fatalities could have been prevented if people would have been informed properly and had been equipped with protective gear. Many of the firemen went into the damaged building to pump water onto the reactor core without any protective gear. Many of them died of radiation exposure in the following days and weeks. Now, when it comes to the estimated long-term fatalities of the Chernobyl accident, in this study they estimate these numbers that are in this table. So the emergency workers, these are the workers that came in after the accident to start cleaning up and secure the building and so forth. So there about 1,000 people participated, and the estimate is that in that population 180 of these 1,000 people would have or will die of cancer anyway, whether Chernobyl would have happened or not. This is the natural cancer rate in the population, about 1/5. And the increase of cancer deaths because of the radiation is estimated to 20 people. So it's an increase of about 10% of the natural cancer rate, or 2% more of the number of people that participated in the emergency response will additionally die of cancer. The liquidates, these are cleanup workers that started removing soil around the reactor area and other cleanup activities. These were 650,000 people that were rotated through. Here the natural cancer rate would be 90,000, and the estimate for cancer deaths related to the Chernobyl accident is 2,000 of the 650,000. So 0.3% more of the people participating in the cleanup will die of cancer because of their radiation exposure. Similar additional risks are estimated for the people who lived directly in the village around the reactors, or in the small town around the reactor. 115,000 people were evacuated, and also here, because they were not informed and they stayed in the area for much longer than they could have, they received a fairly high radiation exposure, and they will also suffer a similar fate as the cleanup workers. The residents in the high zone, this is an area that did not get evacuated because the radiation levels were lower, but still the radiation level was much higher than natural background radiation. They have a similar risk because they, at lower radiation, just stayed there much longer. So we see that there is a statistically significant increase of cancer deaths because of this accident. We can add them all up. So this is 3,420 unfortunate people that will be exposed to cancers that otherwise wouldn't have. So there are clear risks with nuclear technology, and safety, of course, needs to be a very big consideration when building these plants and maintaining them. We saw on the previous slide that nuclear power definitely has risks. People die. Like with any technology, things go wrong. But we also saw that the record of fossil fuel-based power generation is much worse. The supply chain of fossil fuels and the actual use of fossil fuels apparently poses much more risk than nuclear power use. The number of deaths per power output is much higher for fossil fuel-based power generation. Nuclear power also shows clear advantages when it comes to overall public health. This is a graph from the Goddard Institute of Space Studies, and here they plot the cumulative prevented deaths in millions for the world and various regions of the world between 1971 and 2009 by using nuclear power. So they say that about 1.8 million people did not die because nuclear power was used for electricity generation instead of fossil fuel power. And the reason for that is that nuclear power plants emit practically no pollutants because they have no exhaust fumes. Coal-fired power plants continuously feed coal through them and burn it, and so out of the smokestack there is a continuous flow of pollutants which include carcinogens and particulates. It is clearly demonstrated that these pollutants cause respiratory illnesses and lung cancer. Another interesting fact to consider is that the fly ash emitted by coal-fired power plants carries 100 times higher radiation into the surrounding environment than a nuclear power plant with a similar energy output. The reason for that is that coal contains traces of thorium and uranium, both radioactive, and the burn process concentrates these radioactive elements in the ash that is coming out of the smokestack. In fact, they measured the radioactivity in people's bone marrow who live around coal-fired power plants. In fact, they did an experiment where they measured the radiation doses coming from people's bone marrows in areas around coal plants and comparable nuclear plants, and they found that these people have about 50 to 200% higher radioactivity levels in their bones when they live around the coal-fired power plants and also eat food that was mainly sourced from the region around the coal-fired power plant. So we see that as long as nuclear power does not have an accident, it is much advanced over conventional fossil fuel power in terms of pollution and overall cleanness. I thought it would be instructive to consider the nuclear accident at Fukushima that occurred in March of 2011. Here you see a picture of the facility after the disaster had its way. There were 4 reactor buildings. There are actually 2 more, they are over here, but they were shut down at the moment of this accident, so only these 4 reactors were affected. And so you see that 3 of the 4 buildings are pretty much obliterated, and this is what happens when hydrogen explosions occur. Hydrogen develops when water that is used in the cooling system gets so hot that it starts to react with the zirconium claddings of the fuel rods, and then the water splits into zirconium oxide and hydrogen gas. And the hydrogen gas then accumulates, and when there's more than 4 or 5% of hydrogen in the air, an ignition source is enough to blow everything up. So the way this happened is that an earthquake happened away from the Japan coastline, and after that earthquake, the reactors shut down as they were programmed to do. So the control rods went in and the chain reaction went subcritical. And so everything looked pretty good at that moment. But then a powerful tsunami, which is a big wave, a big solitary wave that hit the coastline of Japan, and also this reactor inundated the emergency power generators that were providing cooling for the reactor cores after the earthquake interrupted the electrical power supply. These diesel generators were flooded with about 6 meters of seawater. They were located pretty low in these buildings, And after that, there was only some battery power left over that provided cooling for a few more hours, but then after that ran out. The cores, even though they were subcritical and the chain reaction was interrupted, but there was still so much energy released that these cores got so hot that the zirconium reaction started and hydrogen was produced, and then the buildings blew up. Let's have a closer look at this disaster. This slide shows a schematic drawing of one of those reactors. All 4 reactors were built in the same way. Inside, at the heart of the reactor building, we have the reactor pressure vessel. This is where the chain reaction happens. It is filled with cooling water. The moderator, this is the primary cooling cycle that circulates the water through the pressure vessel. This is how the energy is being extracted, that is being released by the chain reaction. The pressure vessel is surrounded by the containment. So this is a secondary containment in case pressure gets too high inside the pressure vessel and steam has to be released. This can be captured by the containment and condensated into these condensation chambers that are below. So this is a safeguard against releasing highly radioactive material from the primary cycle in case something goes wrong. Now this is surrounded by an initial concrete containment, which is surrounded by the reactor building. Up here, this is what they call the service floor. So there is a big crane with which one can get the fuel rods from the reactor after removing the lid. When it's shut down, one can get the fuel rods out and then lower them into these spent fuel pools. They like to keep the spent fuel pools close to the reactor because it is dangerous to handle these fuel rods right after they are extracted from the reactor, because they are extremely radioactive and still produce a lot of heat. The easiest way to deal with them is to simply get them out here with the crane and then lift them over here and put them back into water and make sure that this water is circulated and the temperature is kept at a tolerable level. The damages that occurred in the reactors were that reactors 1 and 3 had hydrogen explosions up here because of hydrogen that was released from the overheating reactor cores. Reactor 4 had a hydrogen explosion up here because the water was lost in the spent fuel pool and some fuel rods overheated and then hydrogen was produced and again an explosion. So these 3 lost their roofs. And number 2 had a hydrogen explosion in the containment area that apparently cracked the condensation chamber. But the details are apparently still not clear because it is difficult to examine these spaces because of high radiation and debris. Here's the sequence of events that led to the failure of reactors 1, 2, and 3. After the pumps failed, when the batteries were drained, the temperature in the cores of these reactors started to rise because there was no more coolant circulating. That in turn rose the pressure inside the reactor vessel. The only option that the operators had at this point was to open a valve that would allow the steam to be released into the containment well. And the idea behind that is, of course, that evaporation costs energy, and so if you let the water evaporate, energy is being drained from the core and that will slow down the heating. The price for that is, of course, that the water that's in here is ending up down here in the containment well, and at some point the water level goes below the fuel rods, and that is the moment when things get really complicated. The main objective during any nuclear reactor accident is to prevent a core melt. When the temperature gets too high inside the reactor pressure vessel, the fuel rods start melting and burning at the same time. The molten material drips down to the bottom of the pressure vessel, which is made from steel. Because of the very high heat, they can melt through the steel, and then the highly radioactive matter drips into the containment well. That is the moment when a large-scale breach of the containment can occur and significant amounts of radiation can be emitted into the environment. In this context, the venting of steam from the reactor core can only be viewed as a last gap desperate measure because it only buys a little bit of time before the temperatures get too high and the melt occurs. So as the fluid level dropped further, the fuel rods were exposed and not cooled anymore, and that led to an increase of their temperature. They estimate they reached about between 1800 and 2700 centigrades, depending on which reactor is considered. And at these temperatures, the zirconium cladding of the fuel rods begins to burn in the steam, and that dissociates the water. The oxygen in the water reacts with the zirconium and hydrogen is released. And now we have a situation where the pressure is increasing rapidly in here and the gas inside contains a lot of hydrogen. So at that point, the pressure is rapidly increasing in the secondary confinement, in the containment well, because we're still venting steam to try to keep the pressure as low as possible. But nonetheless, it's rising, and so at 8 bar, apparently, the pressure needs to be released into the environment to prevent the containment from exploding. And that's what they did. So there's another valve that one can open, and this releases the steam hydrogen mixture from the reactor core into the reactor building. At 4% hydrogen content, air explodes with the help of an ignition source, and that is what happened finally in those reactors. You see here in this aerial shot, reactor 1 and 3, they lost their roofs, and reactor 2, which apparently had the explosion inside the containment well, there the roof stayed intact, but the containment well apparently developed a crack in the water reservoir below. In the end, all 3 of these reactors suffered a core melt accident, and in reactors 1 and 3, some or all of the fuel, nobody knows at this point, ended up in the wet well below, so it really melted through. Reactor 2 apparently did not get that hot, but the containment well has a crack, so radioactive cooling water is leaking out. The situation in reactor 4 was different. Reactor 4 was under replacement of the fuel rods, and prior to the earthquake they had extracted the fuel rods and stored them into the spent fuel pool. During the earthquake, the pool developed a crack and the water ran out, and that resulted in an overheating of the fuel rods and release of radioactive material and the production of hydrogen gas, similar to what happened in the cores of the other reactors. And this reactor also had an explosion that blew the roof off. After the hydrogen explosions obliterated the buildings, there was no more barrier to prevent the radioactive material to release into the environment. We see here on this map how the radioactive material was deposited around the reactor site, which is here. Japan was lucky during the event that the wind was blowing in eastern direction. On this picture you see the plume of radioactive material as it made its way east towards the Northern American continent. So here after 3 days in the middle of the Pacific Ocean and then 6 days, the first traces of the material could be measured in Canada, and then after 10 days it reached the United States. And so the amounts of radioactivity, they were measurable, but of course very dilute because of the wide spread of the material after that long journey. But in Japan, on its landmass, there are areas that received significant amounts of deposited radioactive material. It's highly inhomogeneous because it depends on wind and rain patterns, because rain typically washes such materials out of the air. The result is that we have a highly heterogeneous distribution of radioactivity around the Fukushima plants. The radiation levels that these areas received are multiples of the natural background radiation. The greenish areas, these are the unaffected areas, so they show the background radiation, which is smaller than 10 kilobecquerel per square meter. Now if you look at the highest contaminated areas close to the reactor, we have factors of 100 or 3000 or even higher than 3000. These areas are clearly areas where people need to be evacuated. Radiation contamination is different from fossil fuel related contamination because they can permanently contaminate a large area and make it uninhabitable for humans. In the case of Fukushima, this meant that the red and yellow areas shown on the previous slide needed to be evacuated. The area close to the reactor, shown pink, was evacuated immediately after the accident occurred. The yellow area, called deliberate evacuation area, was evacuated within a month after the accident because here the dosage was lower, but the officials worried that people would accumulate a dangerous dose if they would spend too much time in this area. About 62,000 people were displaced. If they were ever to come back to this area, the area needed to be decontaminated. In many cases, this means that a layer of topsoil has to be removed to reduce the levels of radiation. An issue with decontaminating is that the contamination is very inhomogeneous due to wind and rain patterns. This means that the entire area needs to be thoroughly investigated and characterized to avoid undetected hotspots that could later on endanger people after they return. This map shows where the people displaced by the disaster in Fukushima were relocated to. And you see they are distributed across all of Japan. This means that formerly tight-knit small communities were completely disintegrated and the people were distributed over a large area. The loss of their property and contacts to their hometowns resulted in illness and suicide. They estimate now that about 1,600 of these evacuees died because of disaster-related causes. This number has surpassed the number of those killed during the tsunami. On this photo, you see a typical temporary housing complex where the evacuees found shelter. Now, several years after the accident, many evacuees still live in such housing complexes because not enough new housing was built for these people. If these contaminated areas are ever to be inhabited again, the reactor sites need to be cleaned up. The most pressing items are, of course, to remove the radioactive material from the molten reactor cores and the storage ponds. The difficulty lies in the still very high radiation levels and the heat that is still produced by this material. Human beings can only be close to these buildings for a very short time. This makes it necessary to develop advanced robotics systems. The arbitrary shapes of the molten reactor cores that have now solidified in the containment wells makes it very difficult to extract this material because it has to be cut into pieces before it can be carried out of the buildings. Another issue is that the reactor cores still need to be cooled with large quantities of water. This water is leaking out. The same applies for rainwater that is incident on this site. So there are large quantities of water that are contaminated and that are coming out of this area. They try to capture this water and store it in these tanks that you see in the back, because this water has radiation levels that would make it unsafe to let it escape into the sea or into the groundwater. One way to limit the water that is contaminating the ground around these plants is by putting a frozen wall around the reactor site. The plan is to build huge refrigeration sites that can permanently freeze the ground in a perimeter around the plant. When it comes to cost and duration, at this point nobody knows. Estimates are that the cleanup will take decades, and when it comes to costs, it is obvious that it will cost many billions of dollars in order to clean this site up. To give you a sense of comparison, here is a list of some fossil fuel related disasters. When it comes to coal, most fatalities occur in mining operations and the number of casualties can be huge. This has gotten better in the last decades because of better safety precautions. So the numbers are not in the thousands anymore, but more in the hundreds in recent accidents. When it comes to gas, explosions are the main hazard. There was, for example, the Piper Alpha platform that was completely obliterated when a gas fire entered the main pipeline to this platform. This caused 167 deaths. In the Urals in Russia in 1989, a train got blown up because gas leaked from a pipeline and sparks from the train ignited the gas. That costs between 600 and 800 deaths. In oil, the biggest hazard is spillage and fires. Here are some images from the Amoco Cadiz accident that contaminated a large piece of coastline in northern France. When the tanker broke up, 250,000 tons of oil spilled. A similar accident happened in Alaska when the Exxon Valdez tanker in 1989 spilled 40,000 tons, which contaminated 1,600 kilometers of coastline. Most recently, there was the BP oil spill in the Gulf of Mexico, which resulted in 11 deaths and 4.9 million barrels that were released. So there is no question that fossil fuel is also hazardous, but one can maybe say that the most significant difference between fossil fuel disasters and nuclear disasters are that the nuclear disaster contaminates large areas in a much more permanent way than fossil fuels ever could. Fossil fuels can fairly easily be degraded and absorbed by nature, so that after a decade or two, usually the damaged sites have returned to normal, while in the case of nuclear disasters, because of the very long half-life of some of the released radioactive materials, it takes much longer. Furthermore, cleanup efforts are much more complicated because of the highly dangerous nature of radioactive materials. The last few slides of this segment I want to dedicate to thermal fusion. Fusion is a way to release nuclear potential energy without the fuel shortage and waste issues of fission. The technologically most feasible process is to fuse deuterium with tritium. These are both hydrogen isotopes. Hydrogen just has one proton, but hydrogen 2 has an additional neutron, and hydrogen 3 has 2 additional neutrons. So if we take these two nuclei and fuse them, we get a helium and a neutron. This neutron carries most of the energy, and it is absorbed by the breeder blanket, where lithium is transmutated to tritium and heat is extracted from the reaction. Deuterium can be extracted from water. This means there is a potentially, for all practical purposes, unlimited supply of deuterium. Tritium is not present in nature in significant quantities, and so it must be produced through transmutation of lithium. One lithium and a neutron turn into an alpha particle and a tritium. There is another technologically feasible reaction that can be used, which is between two deuterium nuclei. That produces a helium-3 isotope and a neutron. The helium-3 isotope is lacking one of the neutrons, so we only have 2 protons and 1 neutron. The advantage is that we don't need tritium from lithium, but the reaction also releases 68 times less power while needing higher temperatures and pressures to overcome the activation energy. So why is it so difficult to achieve thermal fusion? Why don't we have this type of reactor everywhere and make the electricity with this interesting technology? The issue is that the reaction between the two nuclei needs to get started by overcoming the repulsion between the positively charged protons. So we have two forces that are in play here: the repulsion between the two positive protons and the attraction between the nuclei by the nuclear force. The issue is that the nuclear force has a much shorter range than the Coulomb forces. The energy that's needed to press the two nuclei together is about 10 kiloelectron volts for the deuterium-tritium reaction. This compares to the ionization energy of hydrogen, so which holds the electron to the proton in the hydrogen, which is just 13.2 single electron volts. So we have an about 1,000 times higher energy that is required to overcome this repulsion. This energy corresponds to a temperature of 100 million Kelvin that we need to give these nuclei while pressing them together under high pressure. This is an extremely difficult environment to achieve under Earth conditions. There is no material that can withstand such temperatures, so the entire reaction must be kept floating within a reactor vessel while maintaining the pressure. The Sun is a fusion reactor, and the Sun achieves these conditions by simply being big, and so we have strong enough gravitational forces that the high pressure is produced and the high temperatures occur because of the ongoing fusion reaction. One can essentially say that the challenge with thermal fusion is mainly to recreate sun-like conditions on Earth in a confined environment. Let's assume for a moment we had a working fusion reactor. Where would we get the deuterium fuel? Deuterium is an isotope of hydrogen, and it has an additional neutron in the nucleus. This means that its nucleus has about twice the weight of a hydrogen nucleus. This is the most distinguishing mark between the two, and therefore separation methods based on mass are most suitable to produce deuterium. About 1 in 6,400 hydrogen atoms is a deuterium in nature. So by using a gas centrifuge or a diffusion process or also evaporation, we can separate heavy water that contains deuterium from regular water, and then we can extract the deuterium from that heavy water. So how would a fusion reactor look like? Here we see a schematic. Since there's no material that can withstand this temperature that we need in the reactor, the reaction must happen in a plasma that is contained through strong magnetic fields. The plasma region is surrounded by the lithium blanket that is used to capture some of the neutrons and transmute lithium into tritium. This tritium is extracted from the breeding blanket and fed into the plasma region. Deuterium is added from the outside. That allows to perform the fusion reaction in the plasma. In principle, there is very little radioactive waste. Only the containment that sustains heavy neutron radiation over time transmutates into radioactive materials. Once the lifetime of a reactor is reached, it needs to be treated as radioactive waste. The heat is extracted from this reaction by absorbing those neutrons that penetrate the lithium blanket, and there is an absorber on the outside which simply gets hot, and this heat is used to generate steam and then drive a generator. Current experimental fusion reactor designs use the Tokamak principle. In a Tokamak, we use 3 magnetic fields that confine the plasma on a circular track on the inside of the reaction chamber, and the magnetic field also heats the plasma to a temperature high enough to start the fusion process. There's currently one major research project on fusion reactors. It's called the International Thermonuclear Experimental Reactor, ITER. It's currently built in southern France. It's a collaboration of many countries between the European Union, the US, India, China, Japan, Korea, and Russia. The projected start of experiments is continuously being pushed back. The initial prediction was 2018, but now they are talking of 2020 to 25. The duration of experiments, once it is constructed, is about 20 years. The goal of the experiment is producing a fusion reaction that yields 10 times the energy required to start the reaction. So far, it was only demonstrated that one can start a fusion reaction, but it was never efficient enough to release more energy than it costs to start it. The reaction chamber volume is 830 cubic meter. You see it here. This is the toroid, and these are the magnetic coils. The output power will be 500 megawatts for 1000 seconds. This corresponds to 138 kilowatt hours that are released in these 1000 seconds, and it would cost 0.5 grams of deuterium-tritium mixture. So you see again the amazing amount of energy that would come out of this really tiny amount of material. The current cost projections are now 20 billion. They started out at 12 billion when they started with this project. So you see that all this is highly complicated and that fusion always seems to be about 20 years away. Okay, it's time to summarize. So we learned that nuclear reactions release 20 million times more energy than chemical reactions. That is the reason why nuclear reactors use very small amounts of fuel in comparison to their fossil fuel counterparts and have a very high energy output. Now in fission reactors we use a carefully controlled chain reaction that occurs in the fuel. There is no continuous fuel flow through. All the energy that needs to be output over the period of half a year or so is contained in the reactor at a given moment. We use that chain reaction to slowly release this energy. That may be the principal reason why nuclear accidents always turn out to be major and that it is very easy to lose control over the reactors once things go wrong. In a fossil fuel power plant, we only have a relatively small amount of energy present and we feed in coal or gas on a continuous basis in order to keep the power plant going. So if something goes wrong, all that can explode or otherwise create a disaster is the energy that is present in the facility at that given time. So that makes it usually much less a problem to control such a facility after an accident occurs. Another issue with fission reactors is that they produce a large quantity of radioactive waste, which is a combination of fission products and transmuted fuels and the containment of the reactor. We learned that this waste needs to be safely kept away for about 100,000 years or even longer. And of course that presents a huge cost and risk factor that cannot be assessed at this point to its full extent. In comparison, fossil fuels produce a large quantity of greenhouse gases, and it is pretty certain now that this is the reason for the increasing temperatures and the increasingly strange weather patterns that we are experiencing on our planet. Now, when it comes to the supply of fuel for nuclear reactors, we learned that there is currently only about 40 years of uranium-235 to go around. Now this may change if there's more exploration and so forth, but it is obvious that nuclear energy is far from being a sustainable type of energy. There will also be a Hubbard peak like for fossil fuels. Now we can use breeder reactors and thorium-based reactors and push this 40-year deadline into the far future. We could definitely create a almost sustainable situation with nuclear energy if we chose to go down this path. Another big issue because of the radioactive waste and the possibility of breeder reactors are proliferation. As soon as one learns to process these fuels, one can also make weapons, and that of course is a great risk if this technology spreads to countries that breed terrorism. When it comes to accidents of nuclear energy, they are rare, and we learned that so far the number of casualties per energy that is coming out of nuclear reactors is much lower than what we experience with fossil fuels, so this is clearly an advantage of nuclear energy. But if an accident happens, then large areas around the accident site become inhabitable for decades, if not hundreds of years, which is of course a problem if we would greatly expand the number of nuclear reactors. Every decade or every 2 decades we would make a large area radioactive around the globe, and so this tends to add up if it takes 100 years in order to clean up the radiation. When it comes to costs, nuclear energy is similar to fossil fuel-based plants. However, we don't understand yet how storage and long-term effects of nuclear power plants will affect this cost number. So there are great uncertainties when it comes to the cost of nuclear energy. Now, fusion could alleviate most of these problems because no radioactive materials are produced as waste. Fusion really has the potential to yield a virtually limitless energy supply, but it is still far in the future, and it is not clear if we ever will be able to harness the power of fusion on Earth.
This concludes part 2 of the nuclear energy segment. Thanks for watching.